When calculating the size of parallel service conductors and applying derating factors, it's important to understand which ampacity column to use. In the specific scenario presented, calculating the minimum conductor size for a commercial building with a connected load of 395 amps after demand factors are applied, and where service conductors are paralleled in one conduit, the initial calculation using 4/0 conductors rated at 260 amps in the 90°C column, followed by an 80% derating factor due to 6 conductors in one conduit, resulting in 208 amps per conductor, and then doubling that for the parallel configuration to achieve 416 amps, which covers the 395 amp service, is indeed correct. The crux of the issue lies in understanding why the 90°C column can be used for derating service conductors, but not necessarily for feeders and branch circuits in all situations. The fundamental principle is that the 90°C column is permitted for derating service conductors. However, feeders and branch circuits often require the use of the 75°C column. The key difference lies in the type of overcurrent protection employed and the specific requirements outlined in the National Electrical Code, or NEC. Overcurrent devices such as circuit breakers and fuses are designed to protect conductors from overheating due to excessive current flow. The ampacity of a conductor, which is the maximum current it can safely carry, is directly related to its temperature rating. Conductors are typically rated for 60°C, 75°C, or 90°C operating temperatures. The NEC specifies which temperature rating and corresponding ampacity column to use based on the termination temperature ratings of the connected equipment and the type of overcurrent protection provided. In the case of feeders and branch circuits, the overcurrent devices are rated in amperes and are designed to trip or open the circuit when the current exceeds the conductor's ampacity. These overcurrent devices are commonly selected to protect the conductors at their 75°C ampacity rating, ensuring that the conductor temperature does not exceed this limit under normal operating conditions. The reason the 90°C column is not always used for derating feeders and branch circuits is because the terminations of the equipment connected to these circuits, such as panels, breakers, and devices, may not be rated for 90°C. Therefore, using the 75°C column ensures compatibility and safety. However, service conductors are treated differently because they are typically protected by a main disconnect switch or breaker that is rated at 125% of the service entrance conductor's ampacity. This means that the service conductors can operate at a high temperature without exceeding the safety limits. This allowance is why the 90°C column can be used for derating service conductors, as the overcurrent protection scheme is designed to accommodate the higher operating temperature. To further clarify, let's consider a few specific NEC sections that are relevant to this discussion. NEC Section 310.15 outlines the general requirements for conductor ampacity and derating. It specifies the conditions under which conductors must be derated due to factors such as ambient temperature and the number of conductors in a raceway. NEC Section 110.14 addresses the termination temperature limitations and requires that conductors be selected and installed such that the temperature rating is not exceeded. This section is particularly important for feeders and branch circuits, as it dictates the use of the 75°C column in many cases. NEC Section 230 pertains to service conductors and equipment. It specifies the requirements for the size and protection of service conductors, including the allowance for using the 90°C column for derating. In the specific example provided, the calculation for the 4/0 conductors is correct because the service conductors are protected by a main disconnect that is rated at 125% of their ampacity. This allows for the use of the 90°C column when applying derating factors. In summary, the selection of the appropriate ampacity column for derating conductors depends on the type of circuit, the overcurrent protection scheme, and the termination temperature ratings of the connected equipment. While the 75°C column is commonly used for feeders and branch circuits, the 90°C column is permitted for service conductors when the overcurrent protection is designed to accommodate the higher operating temperature. Understanding these principles is essential for ensuring the safe and compliant installation of electrical systems. To reiterate the main points, firstly, the 90°C column can be used for derating service conductors because they are typically protected by a main disconnect rated at 125% of their ampacity. Secondly, feeders and branch circuits often require the use of the 75°C column due to termination temperature limitations. Thirdly, NEC sections 310.15, 110.14, and 230 provide the specific requirements for conductor ampacity, derating, and overcurrent protection. Let's delve a bit deeper into the practical implications of using the correct ampacity column. Imagine a scenario where you incorrectly use the 90°C column for a feeder circuit when the equipment terminations are only rated for 75°C. In this case, the conductors could potentially overheat under normal operating conditions, leading to insulation damage, premature failure, and even a fire hazard. On the other hand, if you conservatively use the 75°C column for service conductors when the 90°C column is permitted, you may end up oversizing the conductors, which can increase the cost of the installation. Therefore, it is crucial to carefully evaluate the specific requirements of each installation and select the appropriate ampacity column based on the applicable codes and standards. Furthermore, it's important to consider the impact of ambient temperature on conductor ampacity. The NEC requires that conductors be derated when installed in environments with high ambient temperatures. This derating is necessary to ensure that the conductor temperature does not exceed its rated limit. The derating factors for ambient temperature are typically provided in tables in the NEC. When applying ambient temperature derating, it is important to use the correct ampacity column as the starting point for the calculation. For example, if you are using the 90°C column for service conductors and the ambient temperature is 40°C, you would need to apply the appropriate derating factor from the NEC table to the 90°C ampacity value. Similarly, if you are using the 75°C column for a feeder circuit and the ambient temperature is 40°C, you would need to apply the appropriate derating factor to the 75°C ampacity value. In addition to ambient temperature, the number of conductors in a raceway can also affect conductor ampacity. When multiple current-carrying conductors are installed in the same raceway, the heat generated by each conductor can raise the overall temperature inside the raceway. This can reduce the ampacity of the conductors. The NEC provides tables that specify the derating factors for the number of conductors in a raceway. These derating factors are based on the assumption that all of the conductors are carrying current at the same time. If some of the conductors are not carrying current, the derating factor may be reduced. Again, when applying conductor derating factors, it is essential to use the correct ampacity column as the starting point. For example, if you are using the 90°C column for service conductors and there are 6 current-carrying conductors in the same raceway, you would need to apply the appropriate derating factor from the NEC table to the 90°C ampacity value. Likewise, if you are using the 75°C column for a feeder circuit and there are 6 current-carrying conductors in the same raceway, you would need to apply the appropriate derating factor to the 75°C ampacity value. In conclusion, accurately calculating conductor ampacity and applying the appropriate derating factors are critical for ensuring the safety and reliability of electrical installations. Understanding the differences between the 60°C, 75°C, and 90°C ampacity columns, as well as the factors that affect conductor ampacity, such as ambient temperature and the number of conductors in a raceway, is essential for electrical professionals. By following the NEC guidelines and using sound engineering judgment, you can ensure that your electrical installations are safe, compliant, and efficient. Also, consider the voltage drop in the conductors. While the ampacity determines the conductor's ability to carry current without overheating, voltage drop refers to the decrease in voltage along the length of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. To calculate voltage drop, you need to consider the conductor's length, current, and resistance. The conductor's resistance depends on its material, size, and temperature. The NEC provides tables that list the resistance of various conductor sizes. If the calculated voltage drop exceeds the recommended limits, you may need to increase the conductor size. Remember that increasing the conductor size will also increase its ampacity. When selecting conductors, it is important to consider both ampacity and voltage drop to ensure that the electrical system operates safely and efficiently. Finally, always consult with a qualified electrical engineer or inspector to ensure that your electrical installations comply with all applicable codes and standards. Electrical codes and standards are constantly evolving, and it is important to stay up to date on the latest requirements. By working with experienced professionals, you can avoid costly mistakes and ensure that your electrical system is safe, reliable, and compliant. Keep in mind the practical considerations beyond just code compliance. While meeting the minimum requirements of the NEC is essential, there are often other factors to consider when designing and installing electrical systems. For example, you may want to consider the future expansion of the electrical system. If you anticipate that the load will increase in the future, it may be wise to install larger conductors than are currently required. This will make it easier to add additional circuits or equipment in the future without having to replace the existing conductors. You may also want to consider the cost of the conductors. Larger conductors are generally more expensive than smaller conductors. However, the cost of the conductors is only one factor to consider. You also need to consider the cost of the installation, as well as the long-term operating costs. In some cases, it may be more cost-effective to install larger conductors initially, even if they are not strictly required by the NEC. Ultimately, the best approach is to carefully evaluate all of the relevant factors and make an informed decision based on your specific needs and circumstances. And remember that safety should always be your top priority. When in doubt, it is always best to err on the side of caution and install larger conductors than you think you need. It is also important to properly install and maintain your electrical system to ensure that it operates safely and efficiently.